So I want to talk about another statistical approach. It's called analysis of variance. You can see why I'm getting so excited about variance, right? It's even in the name of this one. We don't call it analysis of variance, we call it Anova. Um, and to give us a motivating example, right, we have another questionable scientific result, which is in the mid 90s, there was this collection of papers, mostly from one lab, that claimed that listening to classical music, most notably Baroque music, could make adults or babies smarter. And right, so here is the figure from their Nature paper. It was analyzed by Anova, right? And it claimed to say, yes, if you play adults Mozart, they get smarter. Okay, and it was analyzed by Anova. What's Anova? How does it work? What's it doing? What's going on? Let's find out. Okay, so in order to perform an Anova on the starter, here it is. I've got the raw data again. Uh, our first goal is, like before, to calculate the total variance, because again, we're going to calculate an F value, right? The total variance is, again, it's just the sum of the squared distance from the mean to each data point, right? Which in this case is 605. I say I'm using some statistical jargon here, dependent variable, right? Dependent variables are the things we measure typically. They're our outcomes. And that's because they supposedly depend on the independent variables. The independent variables are usually things that we set up. In certain cases, these two things get hard to define, right? What's dependent and what's independent, because all of them we kind of measure. But conceptually, right, the dependent variable is the thing that we measure and the thing that we're interested in. Okay, so we've calculated our total sum of squares, the sum of squares of each data point from the overall mean. Then we calculate the unexplained variance, which, like before, right, this is the sum of squares of the residuals, the residuals being the difference from the predicted values, right? The predicted values in these cases are just the means of each group, the means of the Mozart group, the means of the relaxation group, and the means of the subjects who didn't listen to anything at all, just listen to silence. So we do that point minus its mean, we square it, we add it to that point minus its mean squared, and go on and so forth and so forth. Calculate all of those, we get 29.37. Now, as I said, F is explained variance over unexplained variance. Just like before, we divided our unexplained variance by n minus something. In this case, we're going to take our explained variation and divide it by something as well. We're going to talk about it later. Just pretend they're not there, right? I just wanted to calculate the actual F value. The actual F value is 6. And again, we do the same trick. We know the distribution of F, right? Under the null hypothesis. If these groups were really just randomly distributed, these numbers were just randomly picked, all from the same population, just random number, random number, random number, random number, random number, what would be the distribution of F? So we do the same thing. Here are our random numbers. There's our means. We calculate F. We put it in a histogram. Sometimes F's kind of big. Most of the times F's pretty small, just like before. We do this 200 times. In this GIF is 200 times, but in reality, some smart people figured out that we could calculate the actual distribution of F if we repeated this an infinite number of times. And so we get the F distribution shown there. And so we put in what is the probability of getting our F value, which I think was 4 or bigger. And as you can see, it's pretty unlikely to get an F value that is that large if there is no difference between our groups. All right. So what this F value tells us is again, it's the ratio of the explained to the unexplained. But in this case, it's essentially asking, are the means of these groups all different from each other? And you need to kind of go and look at it and think about it, and we'll talk more about exactly why it's doing that in the tutorial. But the point is, we calculate our F value, we see that it's large, we see under the null hypothesis it's improbable to get an F value of that magnitude, and so we decide that the null hypothesis is unlikely to be the case, that these data points are unlikely to have all been drawn from the same distribution. Okay, so now we know how an Anova calculates a p-value. What do we use it for? Well, Anovas are used for all kinds of things, right? This is a one-way ANOVA. Again, spoiler alert, we're going to be talking about a different kind of ANOVA in a second, right? And it's to ask if a factor with 3 or more levels affects the dependent variable. What is a factor, right? A factor is some property that can be applied or measured at different levels. So not something that continuously varies, but the opposite, something that has steps, right? So genotype could be a factor, right? You're either you're a wild type, you're heterozygous, or you're a full knockout. Okay, you can't be in between those. You know, gender is or sex is a classical factor. Drug treatment is another factor, right? You're either on the drug or you're not on the drug, or you've got a placebo, a low dose, and a high dose. Species could be a factor, right? Rat, mouse, human, monkey, right? You can't be a half human, half rat. So you use an ANOVA to see whether those factors have an effect on the data. But they can't tell you whether one level of that factor is different from the other level. So for instance, if we were looking to see how a drug affected a rat, a mouse, and a human, and we got a significant p-value with an ANOVA, it wouldn't tell us whether the mouse was bigger than the rat or the human was different from the mouse. It would just tell us that there's something going on there. There is an effect of the rat, the mouse, and the human. There is an effect of rat, mouse, or human on our measurement, but it wouldn't tell you which one was doing which.